Our next speaker is Naoki Yoshida, and he'll talk to us about direct integration of the collisionless Boltzmann equation in six-dimensional phase space.
Okay, it's been a long day today. Two more talks and maybe two more technical talks. I'd like to talk about a little bit different things from the other talks today. By the way, I'm from Tokyo, where we'd like to welcome you all to the next Olympic Games in 7 years from now. Sorry, Spain and Turkey, but we got this portion. Okay, I noticed many other people today. I'd like to organize some meeting if possible, but the airplane ticket would be expensive, unfortunately. Anyway, I noticed many other people were rather proud of the number of particles they used, and here equally, I'm proudly announcing the lowest resolution ever possible achieved. So here is the usual looking lambda CDM simulation, 100 megaparsec on the side. Okay, notice this is a slice, not a projection, unlike you. And this is with 0 particles, actually. Okay, and I tell you what. But before going that, let me review rather impressive progress of the cosmological simulations, starting from early 70s, using a few hundred particles to simulate galaxy cluster formation. And the number of particles people use increasing impressively, like almost an exponential pace. This is a publication here. So I'm sorry if I miss your very nice work, but this is almost like a random collection. So, okay. So nowadays people are using trillion particles to simulate the full universe. Okay. So let me guess and let me give you a prediction. So the number of particles will be 10 to the 30th, maybe in 1 year or so. And will be 10 to the 15th by the year 2020 when exascale computing will be available. And let me guess even beyond that. And we'll finally reach the Avogadro number when I celebrate my 100th birthday. Okay, so what a nice birthday in this case. But let me ask, do you think you will have fun with 10 to the 23rd particles? Let me ask, do you think? Young people. Maybe yes, for sure, for some of you, but I swear I will not, okay? Keep this slide, I swear I will not, never, okay? So I here take a mathematical approach. Let me give you a little bit, okay, just read it through. So, unlike your naive thinking, anybody's simulations actually do not solve this Boltzmann equation. Take gadget. There is no line which solves these partial differential equations. Anybody's simulations actually closely follow the derivation of the collisionless Boltzmann equation, coupled with Poisson equation. Okay, so ideally, it would be nice if we could follow the evolution of the distribution function in 6-dimensional phase space in this way, coupled with this static Poisson equation. Now, is it realistic? This is just an example. We need to configure the 3D, like XYZ, and the 3D momentum space. So to store the distribution function on 64 to the power 6 grids requires 270 gigabyte memory. Nothing today, okay? I show you some examples. But to store the distribution function on 512 to the power 6 grids requires 70 petabyte memory, okay? Not the disk space, okay? But still it's just like a 50 times Sequoia. So this scaling is certainly a nightmare, but I'm going to tell you that, however, simulations with 256 to the power 6 grids are feasible even now. Because you remember, we did many nice things with 256 cube simulations. That was the biggest simulation we had, okay? Now, but before moving on, let me ask another question. What's wrong with the current n-body simulations, okay? This is perhaps your concern. And this question itself is a sort of wrong one, but let me answer. So here I show a very much simple halo merger simulation. This is the simplest. The two king spheres merging together. So this movie is very much boring, okay? But nevertheless, let me show. Get relaxed, it's a very boring movie. That's it. That's it. No fancy jet, no fancy black holes. But if we do, if we do it with precious 2 million particles, and we plot the velocity structure in Vx and Vy, plot the particles in one configuration space, this looks like this. Just a distribution of particles. At the tail of these two spheres, the distribution looks like this. Okay? No surprise. If we do the Boltzmann simulation, we see much nicer, smoother structure like this. Because these two spheres are merging, we see clearly two humps in the velocity space. Even at the tail of these spheres, we see clearly these things. Why is such structure with particle simulations? So what's wrong with this? I don't have an answer, but you must ask. So these particle simulations, do they really? I don't know. Don't worry about computing power because even beyond the exascale computing, in 20 years or so, we can have the zettaFlops computing, about 1 million times the computing power today. So we can push for this approach. So we have decided to do it now, actually last year. So with our friend Koji Yoshikawa at the Tsukuba University, we developed a parallel 6D Boltzmann solver. It's very much simple-minded. Regular grids in both configuration and momentum space. Domain decomposition is done in configuration space. It could have been done in momentum space, but for our conceptual easiness, we did it in the configuration. Scales very well because, as I tell you in the next slide, it's simply the advection problem, but 6 times in multi-dimensions. So it's very much simple-minded. Particularly, we employ the positive flux conservative method, which has some nice features. What is that? This was originally developed by plasma physics people and tested extensively in 1D and 2D test cases, including linear Landau damping, nicely showing this decaying rate. This scheme, unlike other semi-Lagrangian or higher order schemes, this scheme has a rather nice feature such as non-negative. We don't want to have a negative distribution function. It's manifestly conserved and non-oscillatory. That's it. Now, I'll give you some basics. All we want to solve is this. The outlook is very simple, this equation. In 1D, this is a sequence of advection in x and velocity space. Fortunately for gravity problems, this fourth term is simple enough. It's just a gradient of the Poisson equation. Plasma physics people suffered a lot because they usually have this Lorentz fourth term. Okay, so this V term across B term causes a lot of problem because it is essentially the solid body rotation of the distribution function in phase space. But we don't have this problem in this gravity dynamics. Essentially, it's like electrostatic problem. Okay? So we employ a classic splitting method, already 40 years old or so. So we first advect this distribution function in x, if in 1D, and we solve a Poisson equation here to get this fourth term, and then advect in momentum space. Okay? This is just an illustration. I'm sorry? Is this symplectic? Oh, scheme itself is not really, but in practice, after I check, it really is like that in 1D problem and a few other test cases I show later. Okay. But the scheme itself, only in time. But the scheme itself is not really manifestly symplectic. Okay? So imagine this evolving distribution function. It's a very typical example. After some time, the distribution function will be like this. We want to have a nice property of conserved distribution functions. Simply, if we know the method of characteristic, we have this integration over a red curve should be equal to the integration over a blue curve. Mathematically, it's formulated like this. So simply, we essentially, instead of advecting this distribution function itself, we advect this integrated quantity in a manifest way using the method of characteristics. Okay? How well such a method works in a pure 1D problem? This is a box distribution function, x and v. And as you can easily imagine, this box is deformed, conserving this volume. And this shape becomes ever like this stripe shape without phase mixing. This is the result. Of course, this is the simplest simulation in 1D. So we see this initial profile is nicely conserved. We see some initial smearing, but it doesn't last forever. It just keeps this a little bit smeared shape for a long time over a dynamical time. This is a free streaming in one direction. Energy and mass conservation is guaranteed to this level, 10 to the minus 6 and 10 to the minus 5 of the initial value. Now, this is 8 times this streaming time scale. This is the genes instability. You can imagine the Zeldovich pancake thing without cosmological expansion case. So if we add a long wave perturbation, it becomes unstable to form this well-known spiral shape in phase space, Vx and x. Okay? This is unstable case. The other case is collisionless damping. This is pretty much different from what you would imagine. The collisionless damping, but it's not just dispersing. Okay? Actually, the materials moves over tops and bottoms of these potentials, okay, like this. So if we do this momentum decomposition, we see this, for example, this case, the decaying case, we see this damping and fluctuations. I'm pretty sure this behavior is very hard or even impossible to reproduce in particular simulations. But unfortunately, this has no relevant astrophysical phenomena, so that's not very much interesting. Imagine this is like many orders of magnitude damping. We also compare this growing rate and damping rate with linear analysis as formulated by in this complex integration. Okay? So if the system is in the linear regime, it really closely follows as predicted. Just showing the nice feature of our scheme. Galilean invariance, the scheme itself is not manifestly Galilean invariant, but in practice, adding the translational velocity doesn't change the behavior of this system, as shown here. It's no translational case, red curve, and with additional translation velocity. 3D collisionless damping case, this is pretty much the opposite behavior of the gravitational clamping. So we add some perturbations, and perturbations disperse in this way. Mode decomposition, essentially power spectrum analysis, time evolution. Again, each mode follows the evolution as predicted by the linear theory. Okay. Again, I'd like to show you a very cute but boring movie rather proudly, like this. Funny, isn't it? I talk to data. Okay. Another example, collision of 2 king spheres, one Boltzmann solver, one n-body simulation with 1 million particles each. Okay, this is again slice, not a projection. Like this, like this. I allow you to laugh at me, or even smile, just like this. Nevertheless, this is one of the most expensive calculations I ever performed. To get the same velocity, okay, of course this is not a fair comparison, I should say. The particle simulation can be done on your laptop, whereas we need a supercomputer for this. But to reproduce the same nice smooth velocity power spectrum in this area, we would need 10 to the power 11th particles in this for particle simulations. Okay? Just imagine. I wanted to simulate the same thing with this number of particles, but supercomputing center didn't allow me to do so because it's so trivial. Like uniform sphere with 10 trillion particles, and they didn't accept my proposal. You shouldn't compare. You shouldn't use that computing time. Okay. Anyway, so this is just my guess. Somebody please in Europe, somebody please do this uniform sphere and trillion. Now, cosmology part is a little bit tricky because we have Hubble expansion. And we noticed, we found with this canonical formulation, we have a growing momentum space. This is not really ideal, although the formulation itself could be much simpler. So we chose this another formulation, taking this B as AX dot. Then we have almost roughly a constant velocity bound, but we have a difficulty in this fourth term, including velocity itself, with the Hubble expansion. But unlike plasma physics, it's just a linear dependence and no rotation, so we could manage to do it. This is the most recent very new result with 128 to the power 6 simulation. We can even do hot dark matter simulation in a very correct way, not in an approximate way. This is cold dark matter simulations. We see galaxy clusters and large scale structures, so nice. Power spectrum, we did a little bit convergence test, and for some study I couldn't find a reason, but for some reasons, this low velocity resolution produces incorrect growth factor. So we need at least 64 cube velocity meshes, and we are working hard why we get this weird. Perhaps it's just too coarse in velocity space. With our code, we can do this mixed dark matter case in a very correct way, reproducing nicely the Fermi-Dirac distribution for the neutrino part with this thermal motion as a function of neutrino mass. So this is showing the evolution of the power spectrum of the cold component. As you know, in cosmology, by measuring this by observations, this damping factor one can get the mass, the total mass of neutrinos, which next generation surveys are aimed at. Okay. So here, with this technique, we can really accurately follow this evolution. Nice way. To some extent, perturbation theory can do well up to here, but nonlinear regime, they can't. Toward exascale computing, this is a memory requirement. I already told you for 512 to the power 6 grids, we need a 70 petabyte memory, but that will be available soon. Scalability, let me just mention the gravity part is nothing. It's just a Poisson solver with 512 cube, so it's just like a second or so. So most of the time is spent for advection in 6 dimensions, okay? Scalability is rather well. Also, with this rigorous comparison, we could only use up to 1,000 cores. But conceptually, there is no degradation, except when we have many domain decompositions, like 1 or 2 cells. It's essentially, advection itself is a local procedure, so it's not really affected, except communicating. Tools and development, I can think of is, I hope FFT will be available nicely in the exascale era. Next step will be AMR, perhaps. We don't want to really do follow the evolution in this part. So if we concentrate on this part, there will be much gain. And indeed, available AMR technology can be readily ported to this technique. And maybe just speculating, GPU or many-core architecture might help these operations of 1D advection. To summarize, we successfully followed modest size Boltzmann simulations, core performance tested, free swimming, Landau damping, king spheres, and so on, adapted to cosmological simulations, both CDM, hot dark matter. Our ongoing works include warm dark matter and galactic warps, where the particle noises we don't like to operate, and violent relaxation, and so on. And to end my talk, this is the origin of my talk title from a famous quote from Robert Goddard. So that should be the reality of tomorrow. Thank you very much.
If I can paraphrase Josh Barnes, I think that this absolutely has to be the best way to follow.